Right, welcome back to week 4 of Stats Online. This is the last week that I want to be spending on probability concepts, the topic that we've been doing for the last wee while. From next week onwards, I would like us to move on to probability distributions, which is our next external and a relatively large topic to cover. This will include somehow getting your workbooks out to you. The teachers have them with us here, so we'll work on that over the coming week. This week in this video, I just want to go over a couple of final concepts in this topic. As you can see here, it's a little bit different. I've got an excerpt from a workbook page regarding true probability, experimental probability, and theoretical probability. I took the liberty of highlighting just a couple of things down the page that I want to talk about. Feel free to take notes in your own words about what these things mean, because often in an external paper they do like to toss just one question this way, just a small part of an exam, but if you don't have a proper understanding of the difference between experimental and theoretical probability, students tend to become a little bit stuck on that one question. It doesn't always come up, but much of the time it could do. So, true probability, something we almost never talk about at the beginning, because as you can see there, it's unknown. The true probability is the actual probability of something happening, and as mathematicians or statisticians, we're always trying to get close to that, but everything that we do is just an approximation. Even our theories and equations and formulae are all just approximations. So true probability is unknown. The example that they have here is using a coin toss. We have made the assumption that heads and tails are equally likely, but the true probability, given things like the different carvings on either side of the coin, that could mean it's weighted differently, the grooves could affect how likely it is to land on the edge. There are all sorts of factors that could influence this, so it's actually really unlikely that the probability of heads or tails is not 0.5. So they probably aren't equally likely, but we have no idea exactly what that probability is. We can try to analyse a coin to get close, and there are doctoral dissertations about that. There's plenty to look at, but the fact is we do not actually know what the true probability is. So that leaves us to do experiments and to come up with theories. Experiments, exactly as it says, we're running an experiment to do observations, to run tests, to see how close we can get. So in the same example, that's actually tossing the coin. The key is with an experimental probability is that because we're looking at a number of trials, the larger that number is, ideally, the closer to the experimental probability will be to the true probability. So that is to say, if I only tossed the coin once or twice, I might get heads both times. So if I got heads twice out of 2 tosses, 2 over 2 is of course just 1, simplified. That is nowhere close to what we're hoping would be a true probability of close to 0.5. So the more that I toss the coin, the more that experimental probability should even out. It'll obviously not be exactly what we're looking for. It's an experiment that's subject to many other influences and factors. But the larger the number of trials is, the better our experiment should be. Theoretical probability. Some people refer to this as model probability because we are coming up with a mathematical model or a mathematical theory. So this is where our assumption of 0.5 or equally likely comes in. We have made the assumption that it won't land on its edge and that each side of the coin is weighted the same. And so our mathematical estimate or assumption is that the theoretical probability is 0.5 for heads 0.5 for tails. Now, we're going to look at a lot more theoretical models or distributions of how different probabilities can be looked at. If I just move this page up a little bit, you'll be able to see here a couple of notes about probabilities and models. These ones here that I'm pointing to is actually what we're going to look at next in our probability distributions topic. Not everything is as simple as a coin toss to come up with a theory for, or a model. Here are names of a few others that we'll be looking at. We'll look at each and every one of those in our next topic. Also remember that when I'm talking about a mathematical model, I could be talking about most things we've done so far, perhaps just not in the context of probability. Our bivariate internal was all about coming up with a suitable model for our raw data. And you should all be very familiar with the fact that those models that you came up with, those equations to fit the data, should always be talked about in context. On their own, they're no good. Sometimes in your data, the model just didn't fit well. The same can be said of probability. Sometimes we just can't come up with a good model that will work every time. In some situations, more than one model may be appropriate, just like in your bivariate investigation, though that was a scattergraph context. Sometimes more than one line looked okay. But in all of these situations, as long as we just recognize that we are approximating and trying to get close to, as I said before, the true probability, recognize that that's the context we're working towards, then we should be fine. Next thing I need to talk about, and again, this will only take a couple of minutes, even less time than what we've just talked about. The only other thing that really could come up in a probability concepts exam is you being asked to graph what a distribution of probability could look like. Again, this is something that we are going to see a lot more of in the actual distributions paper, which will start next week. However, there is a little bit of crossover. So, for example, you might be given a list or a table, as they have here, of probabilities for different events. In this case, they're looking at students passing a particular standard. So, as you can see here, they've got the probabilities listed here in the table, noting, of course, those would need to add to 1. A question in an exam could get you to fill in the blanks if they've only given you part of the information. Goes without saying that this could then be graphed. Bar graph because we've got categorical information, numbers up the side, probability can't go above 1. All of these things add to 1. So if you're asked to graph or come up with a suitable display for a set of probabilities, it may look something like this. The other situation in which this could happen is where you're not given the probabilities in the table. You're given the raw information, the number of people out of our survey or our sample, which, if you looked closely before I moved the piece of paper away, was 400 students. So those probabilities applied to 400 students would give us 96, 188, 92, 24. Likewise, that could also be graphed in a bar graph. Note that we still have our categories of N, A, M, and E along our x-axis, but now instead of probability, we have frequency, how many times, how many students. Both are equally as valid. It simply depends on which information you were given to begin with, the probability or the number of students. So, in a question in a paper, if they have asked you to display this information in a suitable way, this is what they mean. In a bar graph or something similar, they are not asking you to only draw a Venn diagram or a probability tree or a table. This is what they're asking you for, a graph of the distribution. Hope that makes sense. That is everything you need to know in this probability concepts topic. So that concludes my week 4 video. Check the team's post for more.